Okay, everybody, this particular video is going to be a review of probability problems associated with Chebyshev's theorem, the empirical rule, the normal distribution, and the central limit theorem. So basically, the reason I'm putting these together because it's going to be a probability question about a population or a sample and the probability of the next outcome being between two numbers, greater than the number, etc. All right. So we have several scenarios here, and the first one we're going to look at is a probability problem where the only thing we're essentially given is the mean and the standard deviation, and we're trying to find the percentage of the population that is within k standard deviations of the mean. Okay, so again, you're not told anything more than the mean and standard deviation. Nothing like it's a bell-shaped curve or it's a normal distribution. All right. The second thing would be is if the data has a bell-shaped distribution. Then in this case, more likely you're going to be working with the empirical rule and this table given here. And then third scenario, the data is normally distributed. And if it's normally distributed, we're going to go with a z-score. So again, one, are you just told about the mean and the standard deviation? More than likely, Chebyshev's theorem. If you add in the word bell-shaped distribution, the empirical rule. If you're talking about a normally distributed random variable, you're talking about calculating a z-score. So let's get started. In our first example here, the average human gestation period is 270 days. The standard deviation is 9. So we know that the mean, mu, is equal to 270. The standard deviation is equal to 9. We want to know what percentage of gestation periods is between 243 and 297. So if you think about it, we're looking at an interval, 243, 297. Somewhere in the middle is the mean, 270. We're only talking about the mean and the standard deviation. That's all we know. We don't know if it's bell-shaped. We don't know if it's normally distributed. We're stuck with Chebyshev's theorem. So we need to determine how many standard deviations are these 2 points away from the mean. The distance from 270 to 297 is 27. Likewise, the distance between 243 and 270 is 27. If you divide this by the standard deviation of 9, you get that you are 3 standard deviations from the mean. So based upon Chebyshev's formula, I'm going to erase this here because we now have k. Chebyshev's theorem is now saying that at least 1 minus 1 over k squared percent of the data is going to be between these two numbers. We found out that k is equal to 3. So when k is equal to 3, this turns out to be 8 over 9, which is 88.9% of the data is between these 2 points. Moving on to our next problem. In our second part, we're now saying the population has a bell-shaped distribution. Since we're working with the same interval here, 243 and 297, we know that we are within 3 standard deviations of the mean. And since it is bell-shaped, we can go to the empirical rule and notice that if we are within 3 standard deviations, it is telling us that 99.7% of the data is between these two numbers. So the answer to this one is 99.7%. So the first one, 88.9. The second one, 99.7. If you notice, this is a much more accurate calculation than if we use Chebyshev's. In the next one, we're now going to a standard normal distribution. a normal distribution. When we're working with a normal distribution, we're talking probabilities, we want to convert to z-scores. In other words, again, we're talking about the percentage of data that's going to be between these two numbers here, 252 and 297. But since we're working with a normal distribution, we want to convert these to the z-score. So we convert these to the z-score. 252 minus 270 divided by 9. 297 minus 270 divided by 9. This one here is equal to a -2, and this one here is equal to 3. So the percentages associated with a -2 and a 3 off of the z table. Let me find that for us. Okay, I don't have this one available right yet, but for 3, 99.87. For a -2, 0.228. Okay? Now, we want to be between these two numbers. So we know that based upon the way the table works, the answer to this problem is going to be 0.9987 minus 0.0228. I'm going to let you take care of the math there, and that would be the answer to C. So again, just to kind of review here right quick, we have 3 scenarios here. 1, we're trying to find a percentage of data between two numbers, something like that. If we're only told about the mean and the standard deviation, we're forced into using Chevyshev's formula. We have to figure out K. If we're told it's bell-shaped, we just have to figure out how many standard deviations go away from the mean. And if it's one of these 3 numbers, we have our answer right there. Otherwise, it's going to be assumed to be normally distributed. You're going to convert to your z-scores. You look up your percentages from the table associated with the z-scores. And then again, based upon what the scenario is, in this one here, we took the higher percentage minus the lower, and right there will be your answer. The next type of probability type question associated with the distribution is the probability about the sample mean being between greater than or less than some number. When we're talking about the probability associated with a sample mean, we're talking about the central limit theorem. So looking at our very first problem here, scores on the final exam are normally distributed. They have a mean, mu equal to 88. Standard deviation sigma equal to 8. We took a sample n equal to 25, and we want to know the probability that the sample mean is at least 84. Well, again, we're looking at a probability associated with the sample mean. That tells us to refer to the central limit theorem. The central limit theorem tells us how we can convert this to a z-score. In other words, this is going to be equal to the probability that z is greater than or equal to 84 minus, hold on. Okay, apologize for being interrupted, so I hope I can get where I start off at. All right, so again, I need to convert this using the central limit theorem to a standard normal distribution. So the data value 84 minus the mean. The mean here is 88. Then we got to divide that by the standard deviation, which is 8. Then that's being divided by the square root of n, which is 25. Now, if you do your math, this is the probability that z is greater than or equal to negative 2.5. Again, this is going to be 1 minus the probability of z being less than or equal to minus 2.5. If you look that up in the table, and you'll get your answer, and your answer is going to come out to be 0.0062. So again, look that up in your z table, and then the answer is 0.062. Moving on to the next question. A pediatric clinic sees an average of 42 patients per day with a standard deviation of 4.9. A sample of size 39 is collected, and we want to know the probability that the mean number of patients in this sample will be between 41 and 44. So again, we're looking at the probability of a sample mean. We are talking the central limit theorem. So from the information, we get mu is equal to 42, sigma is equal to 4.9, n is equal to 39, and we want the probability that x bar is between 41 and 44. But the point here is you're looking for the probability of the sample mean being between two numbers. You need to think central limit theorem. You need to think the z-score associated with the central limit theorem. So again, you're going to be doing your conversion. You're going to find the probability of 41 minus the mean divided by sigma. That divided by the square root of 39. 44 minus the mean divided by sigma divided by the square root of 39. When you do the math, you're going to look at and see that this is the probability of being between, I think, minus 1.27 and 2.55. So do the math of this right here and this right here. Minus 1.27, 2.55. Now, going to the z-table, and based upon the scenario this is, it's going to be the higher percentage, 99.46, minus the lower percentage, 10.20. When you do the math, the final answer is 89.26, 0.8926. So, again, the key to this one here, central limit theorem. When to use it, probability associated with the mean of a sample. Okay? So I hope this helps. The last problem was 89.26. Problem before that, 0.0062. And then this one here I asked you to do the math for. And second to the first problem, 99.7, 88.9. Again, I hope this helps. And move on to another video. Thank you.